Well, here's where we left off. First thing, you should have tried these problems yourself, of course. And now I run through them in case you need me to explain anything. And I guess if you don't, there's always that little thing you can slide along to fast forward the video. Anyhow, number 3, I've done some of the same tricks here that I did in an earlier example, where this 8 centimeters is not the amplitude. That would be twice the amplitude. Amplitude is from the center line to either extreme, so the amplitude would be 4 centimeters. Likewise, when it asks for the wavelength would be one complete wave, the top half and the bottom half. In other words, from there to there. And
if these people are in the building, please come to the switch. Either Brad, Elia Green, Colton Cameron, Annie of the Narva, Anna Penteno, Emma Elliott, and Lucy Zigula.
okay, I would have been better off without that, but anyhow, wavelength is twice this, which would be 120 centimeters or 1.2 meters, but taking them in order. Well, first thing it asks for is the frequency. That's basically given right here. 3 shakes per second, 3 cycles per second, exact, however you want to phrase it. That's the frequency in hertz. 1 hertz is 1 cycle per second, or 1 shake per second. So number 3. Oh, I guess I've got the camera aimed at this half of the board, don't I? Number 3. Frequency is equal to 3 hertz. And where I got that from is that's just given information. Period is the reciprocal of the frequency. A third of a second if you like fractions, 0.333 of a second if you're more of a decimal kind of person. The wavelength. As I was saying a minute ago, 1 whole wave would be like that. You've got 60 centimeters from there to there, then the wavelength is 120 centimeters, 1.2 meters. And I explained that a minute or two ago. The amplitude is 4 centimeters, because that's half of the 8 that's given there. And finally, the speed. Speed of any wave is its frequency times its wavelength, both of which I have written someplace further up the whiteboard here. Frequency is there, the wavelength is there. So 3 hertz for F, 120 centimeters. If you put it in centimeters, the speed will come out in centimeters per second, which is not necessarily anything wrong with that, but I felt like having meters, so I converted. And that's the story on number 3. Number 4. Graph represents a sound wave. So first of all, what is the sound's period? Period is the amount of time for one complete vibration. And time is on the horizontal axis on this graph here. So you can read the period right off the graph. Oh, let's just move this over here. This time it's the period because it's seconds along the horizontal axis of the graph, as opposed to back over there where it was meters along the horizontal axis of the graph. So that made this the wavelength. Right there was 0.02 of a second. So that's the period. Part B. You want the frequency. Well, that's the same general sort of thing that happened back here, only the other way around. This one I started out knowing the frequency and then I wanted to find the period. Over here, I start out knowing the period and I want to find the frequency. Just take the same relationship and arrange it the other way around. F equals 1 over T. Part C. What's the wavelength? Wavelength is speed divided by frequency. I think the way it probably says it on your formula sheet is V equals F times lambda. And then you'd have to divide both sides by the frequency to make it into this version here. It says in the question that this is a sound wave. So you can look up the speed of sound. At room temperature, 343 meters per second. If you go outside on a cold day, I happen to be recording this in early February, and it's like around 12 degrees Fahrenheit outside right now. So the speed of sound out there is probably somewhere around 325 or 328 meters per second or something like that. But in here where I am, it's around 342, 343. 50 for the frequency, you divide, and it's 6.86 meters. And the last one. WGCC, the college radio station. 90.7 megahertz. You can tell from the unit that that's the frequency. A hertz is a unit of frequency. Hertz means cycles per second. Mega is one of those metric prefixes. It means a million. So the carrier wave for this radio station vibrates 90.7 million times per second. Find the period. Well, the period would be, this is like third time we've done this now. The period would be the reciprocal of the frequency. And with such a high frequency, well, high compared to what? It's a low frequency compared to visible light, but with a fairly high frequency, it's going to be a pretty short amount of time for the period. 90.7 once again, mega means a million, okay? So 90.7 megahertz for the frequency. Calculators with scientific notation are kind of nice for this sort of thing. 1.10 times 10 to the -8 of a second. Or if you don't like scientific notation, for which I wouldn't completely blame you.
Elizabeth Lauer and Emma Elliott to the main office.
I'm trying to make a recording here, you know. Anyway, no, they don't know, actually. They have no idea that I'm doing this. Well, that's not entirely true either, but they don't know I'm doing it right now. Another one of those metric prefixes. Nano is 10 to the -9. So 11 times 10 to the -9, 11 nanoseconds. That would be an alternative way of expressing the answer. And let's see. Number 5, part B, we want the wavelength. So that's going to be this sort of thing again. Wavelength equals speed over frequency. Radio waves are a form of electromagnetic radiation. A fairly common mistake. I caught somebody doing it just yesterday, actually. A fairly common mistake is they put the speed of sound in here, and then they get something that's nowhere near the correct answer. Radio waves are a form of light that your eyes do not happen to be sensitive to. Very, very long wavelength light, very low frequency compared to the visible part of the spectrum, but it still travels at the speed of light. Where the confusion comes from is people have a device called a radio and they turn it on and sound comes out of it. So they associate radio with sound. But what's going on is radio waves are carrying information that you need to recreate some sound. But just because they carry the information does not make them sound. Just like sheet music contains information that you would need to recreate a sound, but sheet music is not a form of sound either. It's a piece of paper, okay? So radio waves are actually, in a sense, a kind of light. They travel at the speed of light. And they're given the frequency, 90.7 megahertz. Divide those numbers, it comes out 3.31 meters for the wavelength of the radio wave for this particular station. So that gets us down to where it says something about the speed of waves, about halfway down page 34 here. And I think actually yesterday, I already kind of talked about this, how that, at least in the idealized waves that you have in textbooks, the speed of a wave depends on the medium that the wave is moving through, rather than on properties of the wave itself. Different frequencies, different amplitudes, whatever property of a wave you care to talk about, they all move at the same speed. Well, as I think I mentioned yesterday, in the real world, that's only approximately true. But let's say at least the main factors affecting the speed of a wave are properties of the medium, not the wave itself. And the extent to which something like the frequency affects the speed of the wave, well, that kind of varies by which kind of wave you're talking about, to making no difference to a fairly small difference. But well, in the simplified world of an elementary course, anyhow, it's not a factor. So different frequencies, amplitudes have about the same speed. Water waves. We're not going to get into any, water waves are a pretty complicated topic, actually, so we're not going to get into it in any detail. And we'll just say that the main factor, at least, that affects the speed of water waves is the depth. The waves go faster in deeper water. This is one of the things that makes waves break as they approach the shore. You have, as the water gets shallower and shallower, the front of the wave starts going slower, and the back end of the wave, if you have a wavelength of 20, 30, 40, 50 feet, something like that, the back end of the wave is out where the water's still a little deeper, and the front of the wave is coming up to the shore where the water's shallower, and the back end sort of catches up with the front end. And it's even more of a factor with something like a tsunami, where the wavelength can be in the miles. And out in the middle of the ocean, it's just, oh, there's an interesting little bump in the water, and it comes up on shore and it gets big. And there again, it's the back end of the wave catching up to the front end of the wave, because the front slows down in the shallow water. Anyway, sound waves. Oh wait, almost skipped over string waves. We'll look at this one in a little more detail. What we're talking about here, well, I mean, it could be any kind of a string. It could be a clothesline. It could be waves on electric power lines set up by the wind blowing across them. But the usual application here is you're talking about musical instruments. The strings on, of course, they're not really strings, they're actually wires, but everybody calls them strings for some reason. Probably they used to be strings hundreds of years ago. Yeah. So transverse waves on a string. The speed basically depends on two factors. First of all, F here stands for force. This is the amount of tension in the string. And you can, like on a guitar, you would control that with the tuning peg up on the top there. Okay. The more, the tension is the force in the string, and the more force pulling on something, the faster it tends to move. So that's kind of what you're seeing here with F up in the top of this fraction. A larger force makes the wave move faster. The other factor is the Greek letter mu here. That stands for the mass per unit length. And if you've ever taken a look at the strings on, for example, a guitar, the strings for the low notes are fatter. Okay. For the higher notes, you just got a piece of wire. With the lower notes, you've got a second piece of wire wrapped on top of the first piece of wire to make it heavier. And if you've ever looked inside of a piano, they go even further. If you go down to the left-hand end of a piano where the low notes are, they've got big fat wires in there because there's a third piece of wire wrapped on top of the second one. Well, mass equals inertia. Things behave more sluggishly when they're heavier. And so down here in the bottom of the fraction like that, where you've got more mass, more inertia, it slows the wave down. As for why there's a square root in the equation, yeah, I'd have to stand here for 5 or 10 minutes. And it's not a terribly long derivation, but yeah, you probably don't really want to watch me do that. I've got an honest face, right? Or at least I probably do behind this mask. So both of these factors, and maybe I should point this over here. As far as what note you get out of a guitar string when you pluck it, or a piano string when you hit it, the note is the frequency, the fundamental frequency to be precise, something I'll define a little better next week. But the frequency of the sound, well, the frequency that the wire vibrates with is equal to the frequency that the surrounding air vibrates with, and that's what note you're getting. The wavelength of the waves on the string, that's determined by the length of the string. So you want a higher note, you put your finger on the string, it makes a shorter string, it shortens the wavelength, which gives you a higher frequency. More details on that next week. Up here, that's what I was just talking about with the tension in the string, okay? And the mass per unit length. If the guitar or the piano or whatever instrument it is, a harp, you name it, if it's a little out of tune, you turn the tuning, like it's gone flat, the frequency is a little on the low side. You put more tension on it, that raises the speed, which raises the frequency. So that factor of the string tension is involved in tuning these things. And then, as I said a minute ago, where the mass per unit length comes into it is when you're trying to make a low note, you slow the waves down to give you a lower frequency. So that's kind of how it all comes together in the construction and operation of any kind of a stringed instrument. Finally, a few words about the speed of sound. The speed of sound in general, whether you're talking about the speed of sound in air or the speed of sound in water or any other substance you can think of that sound waves might go through, that's also a formula with a square root in it that actually bears some resemblance. It's not exactly the same, but it has a certain amount of resemblance to the formula for waves on a string. But we're not going to get into that. You can probably look it up in the text. Well, nah, I won't even tell you. If you want to know, we can talk about it another time. Anyhow, if the medium is air in particular, okay, if you take that more generalized formula and you put into it the properties of air in particular, then you wind up with this factor of 402 and also the absolute temperature, the number of degrees above absolute zero. In other words, degrees Kelvin, not degrees Celsius. So if you put in, I forget, 19 or 20 degrees Celsius or something like that, you get that 343 that we've been tossing around in some of the problems we've been looking at. Other temperatures, you give you other changes in the speed of sound. So one more sample problem, and that'll take care of section 9. I'll pause it while you work on that. Okay, so by some other calculation that I didn't include here because I didn't want the question to be too long, It was determined that on this particular string, 240 meters per second would be the correct speed to produce the frequency you want, the correct note. So then, given that, how much tension should it be under? Well, speed of transverse waves on a string is that, like it says just a little further up the page above the question. F is what's being asked for. We have to get numbers to put in. Well, we have V and we need to get a number for mu. As with most kinds of problems, you can put in the numbers first and then do the algebra, or you can do the algebra first and then put in the numbers, and it doesn't really make any difference in the end. I did the algebra first. So to get rid of the square root, you would square both sides. And then to solve it for F, you would multiply both sides by mu. So V is the 240 meters per second that was given in the question. Mu is mass per unit length. The linear mass density, if you want to give it a more impressive sounding name. We're told that 0.8 meters has a mass of 0.0028 of a kilogram. Well, actually, we were told how many centimeters and how many grams, but as with many other things we've encountered, you want to convert to standard units. If you want the force to come out in newtons, a newton is a kilogram meter per second squared. So you have to put the proper units in if you're going to get the unit you're expecting out. So you divide, and the mass per unit length is 0.0035 measured in kilograms per meter. So that goes in there. V was given. (202 newtons), somewhere in the general neighborhood of 45 pounds on just this one wire. I suppose something I could mention as a little footnote is a piano has a whole lot of wires in it. And if each one, if something like 40 or 50 pounds is a typical tension to have on each one of them, that adds up to several tons of tension trying to make the piano collapse. And to support all that, you need a fairly massive frame for it to be strong enough, which is the reason pianos are such a terrible thing to try and move. Those things are heavy. They're worse than refrigerators. So that brings us to the end of Unit 9.